To round out this chapter, we're going to look at some examples of quotient groups. And I have two examples in mind that seem like they are fundamental for our purposes. The first is to really just a basic example that connects our concept of quotient group to some notation that we've been using since, almost the very beginning of class. I've been writing Z mod NZ for modular arithmetic. But the time has come to explain that this is a G mod H in the sense of quotient groups. This will also answer the question of what I mean by setting something equal to 0 or the neutral element in a quotient. So let's review the setup. To do quotient groups, we need a group G and a normal subgroup H. Well, one of your homework problems is that if G is abelian, every subgroup is normal. And so you guys have ostensibly proven that by now, but let's just convince ourselves that it's correct because it's very simple. So if you have any subgroup H and you want to know that AH A inverse equals H, well, let's say I take some specific H here, right, in this thing. Since this is abelian, that is just A inverse H, which is just H, which is evidently in here. So of course it's true, right? Abelian is just an extremely useful condition. And so in particular, now if G is equal to Z, then H can be any NZ that I want. So these are just the numbers that are multiples of N. So we have, 0 and 2N, and then running backwards, and so on. Worth pointing out is that because G is abelian, we often use additive notation for abelian groups. For cosets, then, we'll often also use additive notation. And so what that means is instead of writing for abelian groups, such as this one, instead of writing HG or HA or whatever, we might be tempted to write H plus G or H plus A or whatever. This is the additive notation. Okay, so with Z mod NZ, how about we make N a specific number here to make it concrete? So let's consider the case of N equals 5. That seems like it's simple enough. So then what are the elements of Z mod 5Z? We know what those are. Those are the numbers 0, 1, 2, 3, 4 under addition mod 5. On the other hand, the elements of Z mod 5Z, this is our convention, right? This equal sign here represents our notational convention, right? Which is how I've been using this symbol. In light of our previous discussion, what this means is we take the cosets of 5Z in Z. And so, in other words, what I'm saying that we should do is we should have 5Z plus N. Let's use a different letter than N. How about we use I to represent a coset of 5Z in Z? And what are these? Well, I can be any integer we like, but we have an equivalence relation where 5Z plus I equals 5Z plus J exactly when I minus J is congruent to 0 mod 5. Maybe said a different way, if I were to try to choose different elements of I here, for example, if I choose I to be bigger than like 4, 5Z plus 7 equals 5z plus 5 plus 2, but 5 belongs to 5z. That is a group element. And so that's the same thing as 5z plus 2. And nothing would prevent you from enumerating through the possible elements of z and writing down a little group table. In fact, Pinter actually does this in all of its great detail. And you see, after working all of this out, that the cosets are just exactly the same modular arithmetic table as for z mod 5z. Actually, I'm realizing that I think he uses a different one. Maybe it's like z mod 7z or something, but I don't think that matters. I don't care. That the group table that you get is exactly the same, precisely because that notation is chosen to capture the idea of doing a quotient group. Okay, I want to show one more example that I think is a little bit more abstract, but actually, oh, hold on. There was another comment. Remark. This is why quotient groups set subgroups equal to 0. That was what I wanted to clarify. So if you have some random element of z, how about 18? 18 is a perfectly good element in z. Last video, we saw how to use the natural homomorphism, the projection homomorphism, z to z mod 5z, by taking 18 and sending it to its coset. So the image of 18 is 5z plus 18, which is the same thing as 5z plus 15 plus 3. 15 lives inside of 5z, so is just absorbed. You get 5z plus 3, or if you like, this is the equivalence class of 3. And we said we'll write equivalence classes with boxes around them in z mod 5z. And so what happened is the original element, 18, is broken down into its coset part and its sort of non-coset part, if you will. And this is removed. What you get is the equivalence class of this thing is 3 in z mod 5z. I want to be clear that it's not really 0 in the sense that this equivalence class is the same as this equivalence class, but this is kind of the process here, is that we do the division algorithm, right? 18 equals 5q plus r. And then we throw away this part, and the remainder is what becomes the equivalence class representative, if you will. Okay, glad I didn't forget that. Another example. These are called commutators. And I think in the first video, I hope I said this, I intended to say this, is that quotient groups allow us to pick groups apart into simpler pieces. And in particular, they let us remove pieces that are possibly undesirable. So by now, I'm completely sure that you guys agree that abelian groups are nice and easy, and non-abelian groups, I mean, it depends on the non-abelian group, but it's never better to be a non-abelian group than to be an abelian group when you want to do math, right? Like, it's always better to have an extra property than not to. And so commutators, and in particular, the commutator subgroup, is an object which measures how far away a group is from abelian. So let me tell you what these are and how the corresponding group is defined. So let's say we have a group G, possibly non-abelian. We can think about elements of the form AB, A inverse, B inverse in G. Why would you want to think about this? Because these things are equal to E if and only if AB equals BA. You can see that by multiplying both sides on the right by B and then multiplying on the right again by A reverses the direction. And so the idea is if I have some general group G, it will usually not be the case that AB, A inverse, B inverse is probably not equal to E because most of the time group elements don't commute. However, if I could form a suitable quotient group, I could insist that this be equal to E by setting that quotient group to be the coset of the identity. So in other words, we are led to search for a normal subgroup which contains all expressions of the form A, B, A inverse, B inverse. And these such expressions are called commutators. And then if I had such a normal subgroup, which we could call H, then G mod H sets AB, A inverse, B inverse equal to E because the things in here now would live in the coset of the identity because they live inside this group H. So therefore, G mod H would be abelian. And that would obviously be a huge simplification to know what, if I needed to do a calculation, it would be a resource. I mean, to be clear, you can't just decide, I have a calculation I have to do in G. How about I do the calculation in G mod H instead? What happens is there are many situations where the calculation that you want to do in G does not depend on the commutativity. And so rather than do the computation in G, it is okay to do it in G mod H for some other reason. And only under the situation where you know it is allowed to do that can you pass to G mod H and then do a simpler computation. So what I want to do to finish this video off is explain that actually this normal subgroup is very easy to find. So we can consider the subset of G of commutators. It turns out that this is actually already a perfectly good normal subgroup. We just need to sort of unravel a little bit to see why this is the case. So, for example, the identity element is a commutator. Why? Because set B equal to A, right? Then you get A, so A squared equals A inverse, so A squared inverse. Those cancel out and you get the identity. On the other hand, I can just, in order to see that this is closed, well, it won't be in general, it is really what it boils down to. But we can just take as a subgroup, take these commutators as generators for the group we want. Maybe I should say for the subgroup that we want. And this is a nice little trick because what I'm saying is, well, the thing that I wanted isn't closed. Oh, well, too bad. Make it closed. By just taking all possible, not just single elements, but also multiplications of 2 things, of 3 things, of 4 things, and so on, and just like, yeah, toss all those into the subgroup I want too. Well, now if I have the identity element, every commutator, being a generator means I have all the multiplications and all the inverses. So I got them all. And actually, the piece de resistance, as Pinter would say it, to finish this is this subgroup is invariant under all automorphisms. I'm going to put an exclam here because the statement is actually trivial, but it doesn't feel trivial. Let's just try to unravel what it means. An automorphism is a self-isomorphism from G to itself. And what I'm saying is phi also sends H to itself. And there's no reason for an automorphism to do that in general, but this one does. And the reason is because this group is constructed by certain multiplications of certain group elements. And automorphisms, isomorphisms, homomorphisms in general, preserve group multiplication. So commutators are sent to commutators. Probably different commutators for most automorphisms, but who cares about that, right? They just go to some other multiplications of the form A, B, A inverse, B inverse. The A is changed to something new. Maybe we could call it phi of A or C or whatever, but it's still another commutator. And this set H is comprised of starting with all commutators and then closing it under the multiplication. So whatever you end up with, it's in there. And now to finish off, we observe that conjugation, sending a G to any xgx inverse, is an automorphism. That was one of your homework problems. And so in particular, since automorphisms preserve H and conjugation is an automorphism. Oh, we got to squeeze. Conjugation preserves H, which is the same thing as H is normal. So what you see is we've built up all of this language of group theory in order to parse these statements. And what this has allowed us to do is build up a machinery which produces a computational aid for doing calculations in this case, non-abelian groups, when what we're interested in is fundamentally just something abelian. I'm trying to think if I can give a simple example of this that I think we'll all understand, because this video is much longer than the other ones. I do have an example in mind, but I worry that it's a little bit too, I don't know, complicated or messy for this stage of the game. I could try to give it anyway. Maybe some people will appreciate what I'm saying, or maybe not. It's fine. So we recall, let's think about line integrals in vector calculus. When you have two different paths, right? A line integral takes in, you have something you want to integrate. I'll just call it f. And then you integrate it over a path. And this gives you a number. So we take in the information of a path and an integrand, and you get a number. Let's say I fix the integrand. Then we're just talking about varying paths. You guys know that integrals are linear. And so geometrically, it is not the case, or sorry, I should say geometrically, tracing path number 1, then path number 2 is not the same thing as the other way around. And I think we just know that. Just think about like doing your errands or whatever, right? Like it does make a difference which order you do things in if you're like moving around town. On the other hand, the integral, maybe I'll put O plus here, right? For do one, then do two. The integral is linear, it's additive. And that is the same thing regardless of which order you do it in. And so even though we have these paths which are non-abelian, in the sense that the order does matter, integrals are abelian anyway. And so what this is a situation where you can think of this as modding out, or to use a piece of violent terminology, we often call this killing commutators. And since you guys are stuck with me for the next, year or so, we are going to return to exactly this theme when we get to a module down the line in complex analysis, which will show you that this idea of modding out by things, or how do I say this? It's a situation where group theory and this idea of using quotient groups will naturally appear somewhere else in your mathematical life. And my hope is that having seen this now, maybe there'll be a little bit of a brain blast when we get to that in however many months, down the line. We store this in your back pocket till then.